Hello, this is homework 2, part 2. It is October 7th, 3:45 in the afternoon. So for part 2, we're going to derive an expression relating the height of a ball and a rotometer to the volumetric flow rate. A rotometer is a device that measures the flow rate of a pipe or air current by using a ball in a housing, and the ball rises at a higher flow rate. And where the ball is, there are markers on the rotometer that tells you what flow rate you're at. Here are some diagrams of a flow rate. So how of a rotometer. So how would work is you would have a flow rate going up the bottom, and at a higher flow rate, it'll cause the ball to move up more and more and more, and then you would have readings on the sides that would tell you your flow rate. The way this works and what prevents the ball from dropping out is that the sides of this are actually tapered. So we can say that the bottom of the rotometer is actually the width or the circumference of the ball. We'll call that D naught, and then the width at the top is D. So D naught is the width of the ball. So I've imported our velocity function from lecture. If you want to know how we got that, go back and watch lecture. But our equation for flow rate is Q is equal to volume times the area. In this case, it'll be Q is equal to V2 times A2. Like I said, we already know our B2, so we're solving for A2. Since this is a cylinder and we have the diameter, or we are solving, or we know that, it'll be pi d2 over 4. And since it's tapered, it will be pi d2 over 4 minus pi d naught squared over 4. So we can plug that into our equation here. Now, since the rotometer is tapered, we need to take that into account, and we can do that using a linear line, or the function y equals mx plus b. In this case, b will be d naught. And then m times the height of the container. The height is this. D squared would be d naught plus m times h times d naught plus m times h. And excuse me, I keep putting lowercase d's. That's my fault. There we go. So if we factor that out, d naught plus 2 d naught mh plus m2h2. So we can plug this in for d and our d naught, which will give us Q is equal to v squared pi over 4 times d naught plus 2 d naught mh. And we're just going to take care of this now. We know that m is small because the slope of the slope of the taper is very, very small. So m squared would be an even smaller number, very close to 0. So we can just go ahead and assume that that is 0. So we can take that out. So we're not going to include that. And then this is going to be minus d naught. So these d naughts will cancel. So we are left with times d naught plus 2 d naught. I'm sorry. We're just left with 2 d naught mh. So we can now plug in V2, which we know from up here. That is going to be Q is equal to pi over 2. We can pull this 2 out. It'll be pi over 2 times, it was, hold on, let's look, rho B minus rho F times d naught minus g times 4g all over 3 rho F, and that is to the 1/2 power times d naught mh, all of that times pi over 2. Now, when it comes to rotometers, this V2 is considered the constant of proportionality. And is denoted by the letter B. And then we finish out here with d naught mh. So when you go to buy a rotometer, it will actually tell you on the package that your constant of proportionality before you even get it. So that is the equation relating the flow rate to the height of the bead in the rotometer. We also learned about the constant of proportionality. Thank you very much.